Welcome. This video is going to take a look at atomic structure and a little bit at the theory that helped us get to this idea of the atomic structure, specifically that atoms have three subatomic or smaller particles that make them up. So as discoveries were made in electricity and other fields, scientists continued to make discoveries and add to the idea that John Dalton and Democritus had come up with about the atom. And eventually they learned that atoms are not just one solid chunk of matter or homogeneous matter, but they have smaller parts in them, or what we call subatomic particles. And subatomic particles isn't nearly as confusing as it sounds. It just means sub is smaller or part of, so it's parts of the atom. And an atom, they also found under extreme circumstances, can be divided or taken apart, but that would be a nuclear reaction, and I'm guessing you know enough about nuclear reactions to realize they don't just happen and they aren't common occurrences for us. So scientists now know how extremely small an atom really is, and in fact, if an atom became the size of an orange, then the orange in relation to the size of the atom would become the size of the Earth. So that's kind of the perspective. If you think of an atom and an orange, the difference in size is the difference in size of an orange compared to the Earth. So how did they come up with this idea of subatomic particles? Well, again, early chemists thought the atom was a homogeneous or homogeneous particle, just like a solid object, the same throughout. But static electricity between objects made scientists look a little closer at this idea, because they came up with this thing called a cathode ray tube, and I've got a couple diagrams down below. And how it works isn't super crucial to us, but William Crookes was the first to realize that electricity passing through a vacuum, or cathode ray, creates a ray or radiation moving from the negative to the positive end. And when they realized that it's really a stream of particles, and these particles have a negative charge, they started wondering, did it depend on the type of gas? Did it depend on the electrode? And they soon found out it didn't depend on either of these things. So when they realized that neither the type of gas or the electrode affected this ray, it was always there, it was always created, they decided all matter, all atoms must have these charged particles. So then they wondered if the atom had this charge to it, but J.J. Thomson in the 1890s figured out that these small particles were actually smaller than a hydrogen atom. And at that time, we knew the hydrogen atom was the smallest of any of the elements. So this was a huge discovery. It meant that there was a subatomic particle, or something smaller than an atom. So this led Thomson to propose what's now known as his plum pudding model. There's a little picture down here that basically, now he thought the atom was just kind of this homogeneous blob of stuff with these electrons embedded in it. And since you probably don't know what plum pudding is, I think of this as the chocolate chip cookie model. So the electrons were like the chocolate chips, and then the rest of the atom is like the cookie around the chocolate chips. So now that scientists knew there was this smaller part called an electron, or having a negative charge, they started looking at how big is this and how much charge are we talking. And it was Robert Millikan who did some experimenting with oil drops who answered both those questions. And he found out that the amount of negative charge on each electron was just 1.6 times 10 to the minus 19th coulombs. So how small amount is that? Well, a coulomb is the amount of charge, and a volt is when you have that charge moving. So volts and coulombs, you can kind of think of being the same thing. And you know, a 1.5 volt battery is not a lot of energy. It doesn't do a lot for you. And this is only 1.6 times 10 to the minus 19th of that amount. So a really, really small amount of charge on an electron. We now think of electrons as having a -1 charge because it balances the +1 charge on a proton. So if electrons are 1.6 times 10 to the minus 19th, protons are 1.6 times 10 to the 19th with a positive charge. So it's just easier to think of each one as being +1 or -1, or that they balance each other out. But when we actually look at it with a unit attached to it, it's a really small amount. Millikan was also able to calculate the mass of an electron, which is also incredibly small, and he came up with it being 9.1 times 10 to the minus 28 grams, which is about 1/2000th as much as a hydrogen atom weighs. And as we'll find out later, a hydrogen atom really consists of just a proton. So electron has very little mass compared to a proton or a neutron. In fact, it's so small that chemists usually ignore the mass of an electron, that when we're looking at the mass of an atom, we're usually just considering the protons and neutrons if we're keeping things simple. So the idea of the nucleus and protons and neutrons followed fairly soon after the idea about the electron was confirmed. And Rutherford was a scientist who was trying to prove that Thomson's plum pudding idea was correct. And so he thought if he shot a beam of alpha particles, which are big, heavy, and positive compared to electrons, so if he shot it through gold foil, which should have these little plum pudding atoms in it, he thought the alpha particles would pretty much go straight through the foil because the electrons are so lightweight and so little charge that they aren't going to affect these big, heavy, positive alpha particles. So he was absolutely shocked that some of the alpha particles were deflected at huge angles. And in fact, some even shot straight back. It was like they hit a brick wall and bounced backwards. And in fact, he was said to have exclaimed that he couldn't have been more surprised if I had shot a bullet at a piece of paper and it ricocheted back at me, which would be pretty amazing. So here's a graphic showing what he expected. So you see the gold atoms. The gold foil just means it's a really thin layer, just a few atoms thick. He shot the positive particles through, and he thought most of them would go straight through, which you see with the straight line. And a few of them might deflect or bend a little bit, and then he would know where they hit by using this detector at the other end. And instead, when he shot the particles through, a lot of them did exactly what he thought, but you notice there's a few of them that actually go backwards, and you can see that, in the upper right there, or I guess it's the upper left, where the one is being deflected straight back. So how did he explain that? Well, he came up with the idea that there must be two things going on, that most of an atom is empty space that the electrons move through. So the plum pudding idea is partially right, but what Thomson didn't know is that there's also a tiny, really dense nucleus in the center. And that would mean that most of those alpha particles went through the empty space area of the atom, but a few of them hit that nucleus, and when they hit that nucleus, that's what made them bounce straight back. So along with Rutherford's idea and various other people in the 18 and 1900s, we've now come up with what we call the modern atomic theory. And it's also known as nuclear theory because we know an atom has a nucleus. So when you hear nuclear theory, it's not this big complex thing necessarily. It's just the idea that atoms have a nucleus. So we've made some changes or revisions from the older atomic theory. We now know they can divide. They don't usually divide, but they can be split into smaller subatomic pieces. And in fact, there's hundreds of subatomic pieces that scientists now know about. But we're going to be concerned with just the three biggest pieces: protons, neutrons, and electrons. And when that happens, when an atom divides, it's a unique reaction called a nuclear reaction. We also now know that atoms of the same element are mostly the same. They have the same number of protons and electrons, but they can actually differ in their number of neutrons, which changes their mass. We call those isotopes when you have a slightly heavier or lighter atom. And much of an atom is empty space in which the electrons move.